it going, everyone? Mr. Geyser here with the first video in our Lesson 13 series for exponential and logarithmic equations and inequalities. For these videos here, we have three main skill and learning objectives. First, we want to use those properties of exponents and logarithms to solve equations and inequalities. Two, when solving these exponential and logarithmic equations, we want to analyze them for any extraneous solutions, meaning that those solutions would give us non-real answers. And in three, we want to use inverse operations to write these exponential and logarithmic equations that reverse the mapping of a specific graph. In our 13a series here, we want to explore the exponential and logarithmic equations and inequalities using this one-to-one property. So let's consider the following equations. 2 to the power of x is equal to 64, and log of 3x is equal to log of x minus 8. We can use these one-to-one properties below to solve these equations algebraically. But how do we handle the more difficult equations and inequalities? For these one-to-one properties here, some logarithmic equations can be solved by changing the exponential form and vice versa with the logarithmic form. What I mean to say is, for any exponential function where f of x is equal to some base of y, if base b to the power of u is equal to base b to the power of v, then that u is equal to v. Whereas long as these bases here are exactly the same, then we know that these exponents here have to also be equivalent to each other. And the same is true for logarithms. For any logarithmic function, if f of x is equal to log base b of x, if log base b of u is equal to log base b of v, then that u and that v, by definition of the property of equality, have to equal each other. As long as these bases are exactly the same, we can assume that the inside of the log here is exactly equivalent. Now, in example 1a and b here, we're going to try out those two properties. For example 1, we're given 2 raised to the power of x minus 5 is equal to 64. I'm just going to rewrite it real quick where I have this 2 in blue and that 64 in red. And what I want to try and manipulate is I want to try and make this 64 into something that has an exponent with the base of 2. Well, I know 64 is going to be one of those factors of 2 where I just do like repeated multiplication. And 64 happens to be 2 raised to the power of 6. Now that I have the same base for my exponential form, I can just say that because of the property of equality for exponential functions, that x minus 5 is equal to 6. And then I know you guys know how to solve this out. I just add 5 to both sides and I get x equals 11. Once you get a solution though, just like you guys did in algebra, I want you to do a quick mental math where you're just plugging that 11 back into that base equation, real quickly doing like 2 to the power of 11 minus 5 is going to be equal to 2 to the power of 6. Well, 2 to the power of 6 is just repeated multiplication. I personally can't do this in my head where I just do 2 times itself 6 times. But I can reason out that 2 times itself 6 times is just 4 times itself 3 times. And I can do 4 times 4 is 16, times 4 here is going to give me 64. Try and do these mental maths whenever you can to double check these problems here. Now, let's take a look at part 2 here. For part 2 here, we're given that 1/2 of log of x is equal to 2 log of 2. I can already see that I have the same log base for both of these parts here, but I don't have the same internal setup because I have this 1/2 and this 2 on the outside of the logs. Before I use my property of equality for logarithms, I need to bring those things back into the actual logs here. And when I bring that 1/2 back into that x there, really all I'm saying, bringing that 1/2 back into that x, that 2 back into that 2, all I'm really saying is it's x to the power of 1/2, 2 to the power of 2. We already know that anything to the power of that fraction there is just going to give me a root with that fraction, that denominator on that outside. What I mean to say is like 1/2 is just the root of 2. If that was 1/3, it would be the root of 3. I know you guys know that. And 2 to the power of 2 just gives me 4. Now that I have this same base on the outside, I can just cross those out and say that the root of x is equal to 4 here. And now I just solve that out. I square both sides and I end up getting x is equal to 16. However, when I plug this back into my problem here, I can't do that mentally. So I need to do a quick calculator check where I'm just plugging in that 16 into that 1/2 log of 16 to get 0.602. And I'm plugging in that 2 times log times 2 into a calculator, and I also get 0.602. So I get the same answer when I plug my x value into that first part of the equation, so I know I'm all good. In example 2 here, we want to try and solve out 24 times 1/2 to the power of x divided by 3 equals 6. First, I'm just rewriting this equation here where I know I want to try and get to the base of 1/2. My first thing to solve for that x in the exponent, I just want to divide out that 24 to both sides, get rid of that 24, and now I'm at 1/2 to the power of x divided by 3 is equal to 1/4. And now I want to try and convert that 1/4 into the base of 1/2 somehow. And I actually know that 1/2 times 1/2 is equivalent to 1/4. And I can just say 1/2 times 1/2 here is equal to 1/2 squared. And now that I have the same base for both of these exponents, I can cross those out and just say, because of the exponential property of equality, that those exponents, that x divided by 3 and that 2, are equivalent to each other. And then it's super easy just to multiply 3 to both sides and say x is equal to 6. Since I have that x equals to 6, let's plug that back into the equation there. If we're plugging that back into that equation there, all I'm saying is 24 times 1/2 of 6 divided by 3 is just equal to 2. So 24 times 1/2 raised to the power of 2 gives me 24 times 1/4 is equal to 6. And I know that that double check is all good. Now let's try and take a look at our logs here. For example 3 here, we're given 2 times log base 3 of x is equal to 3 times log base 3 of 4. For this here, I'm able to say that these red values here on the outside of the logs need to be brought back into the log before I can use that property of equality. What I'm really trying to say here is I'm just trying to convert these 2, or this 2, into a square of x squared and this 3 into a cubed for that 4 to the 4 cubed. Any number, any value that's on the outside of a log that has like that product between it really is just an exponent on the inside of that log. Now that I have these same log bases here, I'm able just to drop those logs and just say x squared is equal to 4 cubed. And now it's super easy for me to do 4 cubed, which is actually in our previous problem, which gave us 64. And I can square both sides, and I end up getting 8, or x is equal to 8. Now when I plug this back into my problems here, I may run into a problem on my calculator where I don't have a custom base, like a log base 3. Luckily for us, when I plug this into our problem, all I really need to do is say 2 times log base 10, the common log that's even on those like dummy blue calculators of 8, divided by log of base 10 of 3 here is the same as if I had that log base 3 of 8, which gives me 3.7855. And if I do that the same with log base 3 of 4 times 3, all I'm saying is 3 times log of 4 divided by log of 3 still gives me that 3.785. They're both exactly the same. I get the exact same kind of answer here. Now that I feel comfortable with my logs and my exponential properties, now we're able to take it up a notch in these next couple of examples. Thank you very much for joining me on this first video of Lesson 13A. I look forward to seeing you guys in that next video. Take care.